Hello there and welcome back. Today we will discuss seafloor spreading and plate tectonics. Before we can delve further into plate tectonics, we must first return back to Marie Tharp's cartography maps. Tharp's maps, as we have had mentioned, showed the mid-Atlantic ridge, which laid the foundation for and supported the concept of seafloor spreading. Seafloor spreading occurs at mid-Atlantic ridges and is where new oceanic crust is formed as a result of volcanic activity, with new magma rising to the surface and cooling to form new oceanic crust. As more research was conducted, it was observed that the seafloor near the ridges were younger than the surrounding ocean floor and further supported this concept. The discovery of these underwater mountains and ridges provided the crucial evidence to support the theory of plate tectonics. Interestingly enough, it was discovered that the ocean floor has a zebra-like pattern with alternating magnetic polarity. Keep in mind that the ocean floor is made of basalt, which is rich in the magnetic mineral magnetite. It was discovered that these magnetic strips of reverse polarity were a result of the Earth's magnetic field reversing, and the magnetic minerals in the basalt would align themselves with the Earth's magnetic field. The ocean floor is essentially a giant timeline. Seafloor spreading at the mid-Atlantic ridge spreads roughly 0.8 to 2 inches per year and is considered to be a slow-spreading center, whereas the East Pacific rise is a fast-spreading center and spread roughly 3 to 6 inches per year. Plate tectonics state that the lithosphere, which is the upper solid layer of the Earth, is broken into 7 large plates and a large number of smaller plates that slide over the asthenosphere. The 7 major plates are the African, Antarctic, Eurasian, Indo-Australian, North American, Pacific, and South American plates. Plates move at different rates and in a rotational manner, with the Pacific plate moving the fastest and the North American plate moving the slowest. The most widely accepted theory for plate motion is that they can move as a result of convection cells, which is the movement of material that is driven by a temperature difference as a result, with less dense material rising and more dense material sinking as it cools. These convection currents are able to transfer the heat from the Earth's interior to the surface. As a result of this motion, the rising asthenosphere can either escape as magma and form new lithosphere, or it can spread out sideways beneath the lithosphere where the plates are located and drags the lithosphere with it and continues to open up these ridges. As a result of the lithosphere spreading and cooling, the weight of the lithosphere is pulled downward into the asthenosphere in the subduction zone. The subduction zone is the zone where a plate is being pulled sideways and downward back into the crust under another plate. The complete mechanism for plate motion is still not entirely known, but a combination of mechanisms is believed to be responsible for plate motion, with these being the most accepted contributions. As we continue discussions about plate tectonics, it is important to mention the stress and strain that is caused as a result of these motions. The Earth's interior is not entirely solid and has areas that have a plastic zone close to the lithosphere, in this area in which the plates move over the plastic asthenosphere. When it comes to stress, this is when an object has force being applied to it, and we can have compressive stress, which is a result of squeezing or compressing. For example, rocks that are located in the Earth's crust can be under considerable compressive stress from the weight of everything above it. Another form of stress is tensile stress, which is when an object is being pulled apart or stretched. An example of this is when with seafloor spreading occurs and the lithosphere is being pulled apart. Then we have shearing stress, which is when the material is being slipped or slid across parallel to the imposed stress. Strain is a result of deformation of the rocks caused by stress and can be permanent deformation or temporary. If the deformation is temporary and returns back to its normal shape after the stress has been removed, this is known as elastic deformation. If the limit of elasticity of an object is exceeded, then the object will be permanently deformed. However, if the stress being applied is sufficient, the object can break before it even undergoes plastic deformation. Between plates, you have boundaries, and they can be either moving apart from one another, known as divergent plate boundaries, moving towards one another, and these are known as convergent plate boundaries, or moving side by side, known as transform plate boundaries. Let's go into more detail of each of these boundaries. In divergent boundaries, the lithosphere is being pulled apart and expresses stress known as tensile stress and are commonly found at oceanic ridges. As the lithosphere is pulled apart, magma is moved toward the surface, filling in any fractures. As a result of plates being pulled apart, earthquakes are common at these locations. Convergent plate boundaries undergo compressive strains as a result of the plates moving towards each other. There are three types of convergent boundaries depending on the location, and you can have ocean-ocean, ocean-continent, and continent-continent. Ocean-ocean convergent boundaries occur when two oceanic plates converge and the older and colder plates get subducted under the younger and hotter plate. This location is marked by a trench where the plate was pushed downwards. The volcanoes above these oceanic plates are known as an island arc. Ocean-continent convergent boundaries occur in a similar manner, and the denser oceanic plate subducts under the continental plate, and in the subduction zone, you have intense earthquakes and volcanic activity. The volcanoes located on these boundaries are known as continental arc, whereas continent-continent convergent boundaries are when either continents or large islands collide, and instead of subducting, they'll smash into one another. This results in the fold belt mountains from our early discussion, such as the Himalaya mountains. Lastly, we have transform plate boundaries, and this is when two plates move past each other in opposite directions and result in intense earthquakes. A well-known transform fault is the San Andreas Fault in California. We'll be continuing on with this discussion in the role that plate tectonics play in earthquakes in our upcoming discussions. Until next time, thank you and have a wonderful day.
1, 2, 3. G.